Hi, I'm Lucas Sheppard, and today I'm going to talk to you a little bit about the ideal and chemical and structural properties of peptoid antimicrobial agents. Antibiotic resistance is a growing and global threat to humanity, and there are many actions necessary to combat this threat. One of these is the discovery of new peptoid antibiotics. Peptoids display many properties which make them more effective than analogous peptides, such as proteolysis resistance. This review will discuss the structural and chemical properties which lend to a peptoid's efficacy and what properties can be optimized to make a peptoid ideal. So search terms like peptoids, peptoid antibiotics, and more were used in Google Scholar, and these papers were taken, structural data as well as antimicrobial efficacy data and cytotoxic data were taken and processed along with structural activity reports to determine what properties lead to a peptoid's efficacy and what properties are necessary. So here we see that there are many peptoids which display broad spectrum efficacy. So that is efficacy against gram-positive and gram-negative bacteria. So here we see in table 1, peptoid 1, pictured below on the top, displays efficacy against E. coli, Bacillus subtilis, Candida albicans, and Mycobacterium tuberculosis. Peptoid C134 MER displays great antimicrobial activity against Mycobacterium tuberculosis. And this is notable because Mycobacterium tuberculosis is notoriously difficult to treat. Here we can also see another table of minimum inhibitory concentration values for other various peptoids tested against the drug-resistant bacteria. So we know also that while displaying broad spectrum activity, these peptoids can be effective against bacteria which have already evolved drug resistance. And we can see with peptoid 32133, 33091, and the following peptoids that the sequence arrangement in each peptoid matters for sure. So let's look at some chemical properties of these peptoids. So the chirality of each side chain didn't really affect the peptoid activity against antibiotics, but it did somewhat affect the selectivity ratio and the hemolytic dose. Lengthened peptoid chains, so making the peptoid chain itself longer, increased the activity against bacteria, but also against human cells. And the shortening decreased that cytotoxicity, but also decreased the antimicrobial activity. It was also found, as you can see in table 3, that the anionic peptoids were almost ineffective compared to cationic peptoids. So the selectivity ratio in the above table 3 displays the dose, it's a quotient of the dose at which 10% of human cells were lysed and the minimum inhibitory concentration for Escherichia coli. It was also found that increasing hydrophobicity had a similar effect to increasing the length, that increased the antimicrobial activity, but also the cytotoxic activity. So peptoids have more favorable in vivo pharmacological properties than analogous peptoids. They last longer in the body and they are not susceptible to proteolysis. Peptoids could also be used to permeate membranes for a synergistic effect with multiple other types of conventional antibiotics. Ideal peptoids should have a net cationic charge per unit length, as well as a low to moderate hydrophobicity, and each peptoid should be optimized for length through experimental testing. But usually, small to medium peptoids are best, as too lengthy peptoids get into the cytotoxic territory. So in conclusion, peptoids have displayed efficacy against drug-resistant bacteria, as well as difficult to treat bacteria. Peptoids have many properties which must be optimized and tested, such as length, hydrophobicity, and ideal peptoids are usually of moderate length, have a cationic net charge, and are optimized experimentally for ideal hydrophobicity. And there are synergistic effects which deserve much further research. I'd like to make an acknowledgement that this research in its experimental stage was funded in part by the Lake Superior State University Foundation undergraduate research grant. Thank you for your time.